Okay, right. I want to talk today about high redshift galaxies identified with the Roman telescope. I'm Ben Holwerda. I'm at the University of Louisville. And if you want to contact me, there's my email and Twitter feed. And so the way we usually identify candidate high redshift galaxies is by using the Lyman dropout technique. So the more, the further the redshift of the galaxy is, the more bluer bands it will drop out of. And so using J and H filters, we can identify with a positive identification there, a clear drop in the Y band, and then a non-detection in a blue or optical filter. We can identify redshift 8 galaxies this way. And it really doesn't go much further than redshift 910 for the HST filters, because H is the reddest it will go. Now, with the Roman telescope, we can actually do a little better. We can go deeper, and not only that, it is meant to go wide. And so there will be many candidate galaxies because we have Y, J, and H, and in fact, there is a slightly redder filter, so we can actually push this out to redshift 11 very likely. Now, we do also have the optical filters to make sure that they are non-detected in the optical. So this will be an ideal training set, the HST images that I'll talk about, to learn how we can do this for the Roman telescope. So as we've been doing this so far is that we have with Hubble the near infrared detections, the optical non-detections, the Y band, intermediate level signal to noise detection. And so that gives us high redshift candidate galaxies. And then we use those images as a prior to identify the photometry with Spitzer that these are in fact high redshift sources. And we do this as follows. The green points on the left are the observed HST filters, and the red ones were the two Spitzer filters. So as soon as we have a Spitzer detection and an H to 3.6 color that is very flat, we can nix other options such as the redshift 5 dusty dwarf galaxy. So they're not as interesting. These were not the ones that we're looking for. We're interested in redshift 8 candidates, and we want to confirm those. And we use 3.6 and 4.5 micron detections for that. It also effectively rules out any T0 brown dwarf or an M dwarf or an L dwarf, or even Y dwarfs, of which there are billions in the Milky Way, and they're also small and fuzzy, and so they would sneak into our photometric selection if we didn't watch out. So using Spitzer is a good way to confirm that these are in fact redshift 7, 8, 9, 10 galaxies. So what do we do now that Spitzer is no longer there? That's the next question. Spitzer gives us an additional piece of information, which is that if there are strong nebular emission lines, these will actually end up in the 4 micron band. So the IRAC colors actually tell us whether or not there is strong H alpha, oxygen 3, and H beta emission. And so Renske-Smit predicted that in 2014, and Guido Roberts-Morsani used that to identify even higher redshift galaxies. So this is roughly how that works. I made a little video where you can see that the bright nebular emission lines go through first the 3.6 and then the 4.5 micron broad filters. And so you end up with IRAC colors strongly tracing nebular emission lines, and that seems to be borne out by the actual high redshift sources that were identified. But now that we don't have IRAC anymore, we can troll through the remaining deep Spitzer fields, and there is deep optical and video field. So it would be interesting to see if we can find any high redshift sources in here. But Spitzer has retired, and we now rely on James Webb to do far infrared confirmation, and that is observationally expensive. So a false positive rate, a high false positive rate, is not a good thing for one of these searches. So are there other ways to cull the selection of candidates down effectively and without biasing ourselves? So we can do visual inspection. That is very common for the high redshift sources that we've been looking at so far with HST. And we can use size or we can use morphometrics. And this is from Joanna's paper where we identified the Y band is 105 and it goes all the way to RAC. And so Morishita in 2018 identified both candidate redshift 9 and 10 galaxies, and he also provided the list of visually rejected or otherwise rejected sources in the Borg fields. And the interesting thing is that a visual rejection looks to be very close to a size criterion. It's not identical to a size criterion, but it seems that if you just applied a size criterion, you could get rid of a fair number of the visually rejected ones. So there is a subset of the visual rejection that is essentially a size rejection. Now, I've been looking at that for a while, and it looks like, yes, high redshift sources at redshift 8 and redshift 9 are resolved by HST. Even in the Borg undrizzled fields, you can see that the green dashed line is what unresolved sources end up being, and the red points are redshift 8 galaxies. So many of them are, in fact, resolved, but not all of them are terribly large. We also looked at redshift 9 galaxies in 2015, and it looks like they're H minus 3.6 color, so the HST versus Spitzer color, or their effective radii seem to select high redshift sources pretty well, and so maybe this could be a stand-in for Spitzer color. That was our original idea, and the IRAC red interlopers are just bigger. They're just larger in size. So this was maybe a good way to, since we now no longer have IRAC, we don't have Spitzer, we can use size instead. We don't want to constrain size too much because we want to measure the size evolution of galaxies. So we can't cut out all the extremes and then still say something sensible about size evolution. This is the super 8s again, so we can see that there is size evolution, and even at redshift 8, they go to about 1 to 1.5 kiloparsec in size. And this is the brightest end of the luminosity function. So we can cut it down to, like, say, 1 kiloparsec, because then we'll miss sizable chunks of our selections. This keeps going at redshift 9 and 10 with the Morishita results and the 2015 results that I added in here as well. And so you can see that we still resolve the brightest sources even with WIC3, and we will do that with the Roman telescope as well. And so we don't want to cut them down in size too much, because we're interested in the size evolution. That is a useful measurement. So if we compare the size evolution at redshift 9 that was predicted by Shibuya in 2015, and we compare that to the histogram of values that we got in 2020 from all the redshift 9 galaxies that we have, and you see that we're dealing with a not exactly wealth of data here, but the histogram agrees pretty well with the log normal distribution that we get at redshift, that Shibuya gets at redshift 6. So it's not a huge change in the size distribution, and it can inform how we should perform our cuts. The thing that I want to point out is that beyond redshift 1.5, it becomes extremely rare to find a redshift 9 galaxy. So this could be a prior for a selection of candidate sources. So in order to bear this out, we look at the luminosity function predictions by Schroeder Mason, and then we use a size luminosity relation to convert that into a size distribution. So now we have a density as a function of size, effective radius, for two size luminosity distributions. One that I found in 2015 for redshift 9 sources, the bright ones, and 2012's Gratian results for redshift 7 sources. So you can see that they're quite different. If we then put in the 0.3 arc second cutoff for redshift 8, if we assume the Gratian result, then yes, we are actually getting rid of a few of the brighter galaxies. If we're assuming my result from 2015, there is no problem. So we have to maybe look at it in a different way. How many of these sources are there total anyway? So we take the number of galaxies that we can have at the volume in the observable universe at redshift. And then so you just integrate over the volume available, and that should give you the total number of galaxies at a particular size. So that's what we plotted here. If I take my 2015 relation, there is essentially nothing bigger than 0.3 at redshift 7 or at redshift 9. If I look at the Gratian result, there are galaxies that are bigger than 0.3, but there's nothing bigger than 0.5 arc seconds. I want you to note that there's these two, the dotted line and the thin dashed line. Those are the points where m star would lie. So your luminosity function isn't particularly constrained by having the 0.3 arc second cutoff. So even if you are willing to take the hit of a few rejections at redshift 9, if you assume that the Gratian result is the actual size luminosity relation, your issue is not going to be with the luminosity function because you already sample it beyond m star. So that could be a viable trade-off. So how many of the bona fide high redshift sources are we missing? Well, if we use the 0.3 arc second cutoff, hard cutoff, and an L star, so the luminosity size relation from 2015, we have the different surveys. We go to a certain depth, so some of them are simply not deep enough to identify or only identify the brightest, biggest galaxies. So how much are we missing if we do this selection? Only for the Borg redshift 9 sources. So essentially redshift 10 and 10 and 11, we start throwing a few percent of them away. In the case of Euclid wide, so this is shallow, we start throwing away up to 50% if we could even identify things out to redshift 16. So really, it's not that big of a problem for the Roman telescope. It doesn't even become a problem until redshift 14. So this could be a reasonable size cut because we would be missing these things probably anyway, given the size of the field and the depth. If we then loosen that up a little bit to 0.5 arc seconds, we will only get an issue if we were trying to do beyond redshift 12 with HST imaging, and as shallow as the Borg survey. So really, there's not much of an issue if you use a size cut or a size prior, provided it starts at about 0.3 arc seconds, and it is the relation from 2015 that we found for redshift 9 galaxies. An alternative could be, or an additional piece of information could be morphometrics. Galaxy morphometrics are numbers put on their appearance. And so we can use the Gini parameter or the asymmetry parameter for in this case, it's the H band. We can also do the J band. They seem to be fairly interchangeable in this case. And my student Zamir Kushmich found that they were not identical to what you expect for the PSF. So the PSF actual point source does not quite look like that in the Gini and asymmetry space. So making use of that piece of the information might mean that we have to have them clustered in this particular point, and the size would give us a good alternative to visual identification of these things, and something that's reproducible over large areas. And so my conclusions are a size cut or prior would reduce the need for a visual inspection and hopefully possibly eliminate it. A size could reduce the contamination of redshift 9 and 10 sources by as much as 60 to 70%. And now that is worth doing. Removal of high redshift sources is negligible for redshift 7 to 13 for the Roman telescope imaging. So I really am not worried about putting the size cut in and biasing myself. This leaves size as a useful measure for galaxy evolution, so we can actually still use it as a measure for how galaxies grow over time, but we can also use it to get rid of the ones that we know to identify sources that are high redshift and get rid of the ones that are interlopers. The morphometrics offer an additional quantity, so maybe then we can also get rid of anything 2-point sourced. And so using both these pieces of information, we're actually increasing the amount of information that we have on a source and that we can use to identify it, from photometry, which is about 4 pieces of photometry, to 4 pieces of photometry and 3 pieces of visual morphology. And I think by combining that, we'll actually be able to identify high redshift sources effectively in large image data sets, such as the ones that we're getting from the Roman telescope. All right, thank you very much. And I hope this recorded properly this time.